I believe we should get started with like purpose. Okay, so yeah, let's get started. Guys, can you hear me? Could you please confirm? Vaibhav, Nikhil, Kripanshu.
Yes, Mayur.
Perfect. Okay. So in last part we discussed about tuples, array, vectors, or how exactly matrix can be defined using primitive data types. Now let's discuss about linked list. So what we discussed about arrays, like array is something where we try to have a collection of elements in contiguous memory location, and for each memory location we just try to have one value over there. Okay. So and this thing is that when you define array, so you try to define so for the first element only memory address is something makes sense. Okay, and for all the elements they will try to take like subsequent memory locations, and that's something. So generally pointer will move from like one memory location to another memory location based on the index attached to that array. So thing is that in case of the array there is just value, and there is means for each of that element there is no sense about where exactly they are and what's the next element. Okay, but in case of the and that's the thing which makes retrieving or like adding or deleting particular element from array difficult. Okay, so that's the reason there is another data structure that has been formed, and that's like linked list. So in case of the linked list, for each element, there is a link, means there is a sense about what is the where is exactly next element is. Okay, and to have that sense of about location of like next element, what generally it used to have with it is like for each memory location, it try to save two things. First is a value, okay, like the value means the information that we want to store in that memory location, and at the same time it will also try to have pointer or link to the next memory location. Okay, and so that's something that particular element is called like node. Okay, so basically for each node we will have like two things. First is a value or information, and second thing is a pointer to the next memory location, and that is true for all the nodes. Okay, so like you will have first node. For the first node it will point to nothing, so we can say like the pointer is like to null. But for second memory location and third and fourth, so for second node, third node and fourth, so what happened, first node will point to second node. Okay, then second node will point to third node, then third to fourth node and fifth node. So thing is that that's how this entire list will form, and basically those each element of that list will be linked to each other using these pointers. Okay, so basically they act as a link between these two elements. Okay, and that's something help us with adding or removing element from that particular list very easy. So let's say if you have to add any element to like array, so means array is kind of like just rectangular boxes which are like put beside one another. Okay, so thing is that in that situation means it, if you have to add or remove element at the middle location, then in that situation we need to move all the elements in like before that element, or we might need to move all the elements which are like after which exist after that element. And that's the reason like this adding or deleting thing becomes quite a problem. And to deal with that thing we can use linked list over there. Okay, whenever we have to add or delete element quite frequently, in that situation we can use linked list very easily. So in case of the linked list, whenever we have to add element, what we need to do, we just need to delete or we just need to cut these links between like previous element and next elements. Means we just have to like delete link between two element, and just we need to put that one new node in between these two things. And for that new node you need to connect that like pointer of like that newly added member should be like pointed to next memory location, and previous element should point to newly added element. If you do that thing, that way we can add any element very easily, and deletion and all that stuff become quite easy with linked list. So thing is that in case of the arrays we have just one element, and it doesn't have any sense about where exactly next element is. Okay, by default it assumes it will be at like a next index location, whereas in case of the linked list, that element itself have information about that thing. Okay, that element itself has information about that thing, like uh, this element, next element will like exist at this memory location. Okay, so that's the linked list. And yeah, so that's something so in the beginning only I mentioned, right, how exactly we are getting, means what flexibility we are getting with particular data structure. That's something defines which data structure to use in that particular application. So this is a distinction between arrays and linked list. I hope these two things are clear to you. The next thing is the stacks and queues. So in case of the stacks, so stack is a collection of element again, maybe in like contiguous memory locations. But thing is that uh, in case of the stacks, each new element will be put on top of previous element. Okay, and the final structure that we will be having would be like similar to that we are having in real world. Like if you observe stack of books, so in that situation, uh, means what we generally do, we try to put a new book on like top of pile of like previous books. Okay, and so we will just like keep piling all the things up, and that's how we like build that entire stack, right? In similar way only, in case of the stack data structure, whenever we have to add new element to that already existed stack or pile. So that operation is considered as a push. Okay. Process of adding new operation to stack is called as a pushing. Process of removing element from already existing stack is called as a popping. Okay. And always addition of element and removal of element will happen at the end of stack. Okay. And basically thing is that like stack is similar to like this sort of thing, right? So so in case of the stack, what we generally do, we try to so we sorry. So the thing is that what we generally try to do, we try to add like new element on top of like previous element, and the next element also on like top of like that newly added element. So that way we try to develop this stack. And process of adding like new element over here is called as like pushing, and process of removing new element from, like previously like element from stack is called as a popping. Okay. Then like here addition and deletion always happen at the top, and that's the reason what we generally do whenever we have to deal with stack, we try to create new variable called top. Okay, so that's something we really don't have to do ourselves. Generally Python programming language handle that stuff. So it try to maintain with a new variable called top, and that top variable in the beginning will be at -1. Okay, so what does it mean is like there is no element inside that stack, so there will be -1 whenever we are adding that element. So basically what we are doing is like we are incrementing that thing. Okay, so it will be 1. So whenever we are doing pushing, it will keep on incrementing 1 2 3 4, and whenever we are doing popping, it will just like increment it by 1. Okay, so that way we will keep like this count of this index. Okay, so basically that's how like we would be able to deal like add or delete element like particular element from stack only. Okay, so the element that you are seeing inside this top variable, so basically that's something will be considered as the index of that particular stack. Okay, or if you represent stack using array, so basically stack and queue both can be represented either using arrays or linked list based on our application. So if we are representing that thing using arrays, so in that situation, the index that we are generating using this top variable will help us to keep like information about like should we what is the current index of that particular element, like, and which element to pop whenever pop operation is called, and which element where to add new element when push operation is being called. Okay, so that's about stack, and this sort of structure will exist over there. Okay, so this is a stacking operation, and sorry, stack data structure, and this stack data structure means we can use like in various applications. Okay, so that's the one thing. Then there is a queue. So queue is yeah. Let me go back to our screen. So that's like about stack. So as I mentioned, in case of the stack, whenever we have to remove any element, we generally remove it from the top only. Okay, so that's the reason the characteristics that this stack data structure follows is LIFO, that the last in first out. Okay, so whatever last element is added over there will be removed first. So that about stack. And in case of the queue, it's again collection of element. It can be represented using either arrays or linked list. The only difference over here is like the property that it follows for like removal of element from that particular data structure or particular collection is FIFO, first in first out. So queue data structure is quite similar to the queue that we see in real world, the one that next to like ticket counter or like vending machine or something like that. Okay, so basically whoever is in that particular queue for longer will be served first. Okay, so whoever is oldest in that particular queue will be served first. So thing is that here are certain terminology that should be that we should understand. So whoever is like first or oldest element inside that particular queue will be considered as a head or front of that particular queue. Whoever is like newest element in that queue will be considered as a rear or tail of that particular queue. And process of adding element to that particular queue will be considered as in queue, and process of removing element is called as a DQ. Okay, and DQ will always happen in FIFO fashion. Okay, so if we consider so if we consider this to be Q, and if we so basically in case of the stack, addition and deletion only happen at the top. Okay, means that's like last element only. Whereas in case of the queue, removal always happen at the head. Okay, so this is like starting position or head or front. So this is a head head element, and this is a tail element. Okay, so in case of the queues, removal or elimination or DQ process always happen for head element, whereas addition always happens at the tail location. Okay, so that's something called as the in queue operation. And apart from that, what we can do in case of the queue is it also allows us to see what element is there at the head location. Okay, and that operation is called as a peak. PWK. Okay, so that's something we should keep in mind. Okay, so that's about queue, and queue follows fashion of FIBO. Okay, so that's the characteristics about queue data structure. And both stack and queue can be represented using means can be built using either arrays or linked list. And yeah, I mean, it depends on what application we want to use that particular data structure for. But yeah, that's the general means understanding, or like that's like information about that particular data structure. So yeah, so that's all about linear data structures. Guys, do you have any question about linear data structure?
No, it is clear for me.
Okay, so let's discuss non-linear. Thank you. Yeah, so let's discuss non-linear or unordered data structure. So in case of the non-linear or unordered data structures, so basically, all the elements in the collection are placed in hierarchical order. Okay. So whenever we try to create this collection, that entire collection will not means obviously it will in the form of one box only. But when we try to create that box, maybe of like homogeneous or heterogeneous element, all the element will not be placed at one level. All those elements will be placed in hierarchical order. Like one element will be like at one level, then there will be a second level, then third level or fourth level. So that's like non-linear data structure. So it's the collection of element where all the elements are like placed in hierarchical order, and that's the reason we call them as unordered data structures. Okay, but that's the beauty of this data structure. Okay, because that's something allows to do like a lot of things with that particular element. Okay, so let's say we have like 50 students in the class. If we go for like this linked list or arrays, then we can just store like one value or one kind of information related to that student. Okay, maybe his age, or maybe his height, or maybe weight, or maybe mark that guy has received in that particular subject. But think, or if we like use like two-dimensional or two-dimensional array over there, then probably we can store a mark for like number of subjects. But thing is that beyond that, we means two levels or three levels. If you go beyond that thing, then that thing will become quite complex, and it's really hard to keep track of all that stuff. Okay, when you deal with like high level matrices, whereas when it comes to like this non-linear or unordered data structures, it's quite easy. Okay, because here all these things are like the hierarchy is something maintained. Okay, at least sense of hierarchy is maintained in data structure, and that's something help us to add any element or remove element, or like search for particular element very quickly. Okay, so basically idea behind this non-linear or unordered data structure is to like include as much as information related to particular element inside our data structure itself. And second thing is, when we have to look for particular information, we should be able to do that search very quickly. So these are like something, these are certain properties that we generally consider when we want to go for like non-linear data structure, or like when we want to decide between whether we should go for like linear data structure or non-linear data structure. But for non-linear data structure, that are the things. So today we're gonna study about set and dictionaries. Okay, so as I mentioned in the beginning only, so basically these are like non-linear data structures which are existing in like Python programming language by default. So set is like unique set of elements, and then there is a dictionary. So that's again key value pair. So you will have like unique keys, and for each of that key, you will have like some information stored over there. Okay, and based on like the hierarchy that you are maintaining over there at one level or second level or third level, based on that you will have like different sort of dictionaries over there. Okay, means you can have like dictionary within dictionary within dictionary, and that's how you can make it like more complex. And means these sort of problems can be solved really easily, because when it comes to decision making, then this decision tree is something help us a lot. Okay, and that's the reason we should study these decision trees really properly. Because later on when you study this reinforcement learning or something, some algorithm related that thing, then you will come across one algorithm called like Monte Carlo tree search. Okay, so that for that MCTS algorithm, this the thing that we're gonna study today is would be like backbone. Okay, will be considered as a backbone for that particular algorithm. Okay. So this is a non-linear data structure where all the elements are at different levels. Today we will study about set and dictionaries. So it's just the key value pair, and basically that's how we are looking at that problem. Okay, so set dictionary, that's how we are looking at that thing. But in order to build that set and dictionary, there are like certain data structures over there. So there is a tree and there is a graph. Okay. And for tree, we can have like certain variations so that we could access a particular element very easily, do that retrieval very quickly. And that's how this binary search tree and heap thing come into existence. And for graphs, there are a lot of things that can be done. Like we can have directed graph over there, undirected graph over there. You can have weighted edges and all that stuff. So that's about graph. And then we have hash maps. So hash maps is something which are built, means which is a combination of dictionaries and hashing operation. Okay, and that's how we are getting hash maps, so that you can do search in real time, or like with constant time. Okay, because thing is that when particular data structure get means too lengthy, so in that situation if you have to look for particular element in such complex data structure like trees or graphs, so in that situation it becomes quite difficult. Okay, but if we use this hashing operation over there, then we would be able to like convert our keys into some unique hash keys, and that something would allow us to like access that element very quickly. And yeah, so that's something would help us to do search operation in constant time. So that's the hash map. So we're gonna see that today. Okay. So let's discuss about sets and dictionary. So you might have studies about like sets during your 11th or 12th, or maybe during first or second year of undergraduate studies. So basically set is a unique collection of elements. Okay, and that's something help us. I mean, if we use set a data structure somewhere, then we would be able to like get rid of like some repetitive element. Okay, because in some cases we really don't want to have like repetitive element over there. So in that situation, if you like use set data structure over there, then this data structure will by itself detect if there are any repetitions or not inside elements, and it will just remove those repetitions. Okay, and that way we will just like get that base set. So that's the set, and whenever we have to define set, as I mentioned in the beginning, that something is built in Python programming language. So whenever you have to define set, we just need to put all those elements inside curly bracket, and that's how we do it. Then there is an extension of set, and I would not call that as an extension directly, but thing is that in case of the dictionaries, what we generally try to do is we try to have key value pair over there. Okay, so you will have some key, or you will have some like heading over there, and for under that heading you will store some information. Okay, so dictionary is a data structure where we try to have key value information intact in one data structure only. Okay, so wherever you invoke particular key, you will be able to get like value attached to that key. So that's the dictionary data structure. So what you try to do is whenever you have to define that thing or whenever you have to declare that thing, what you try to do, you try to put key value pair inside curly bracket only. And for each key, you try to put that thing in like this syntax. Okay, so you will have a key in the beginning, then you will have like a colon, and then you will have like a value over there. It could be like string, it could be some number, or it yeah, it could be anything. Okay, it could be boolean value or whatever. Okay, but that's how you define dictionary. So you will have key and you will have value over there. Okay? So that's about sets and dictionaries. So thing is that whenever we are defining dictionary, the one thing that we should keep in mind is like all the keys that we are using should be unique. Okay, so that's the reason I have put these two things in one slide, because set is nothing but a collection of elements which are quite unique. And when it comes to dictionary, though, that means like it's collection of key value pairs, but all the keys that we are using should be unique in its structure. Okay, so that we would be able to distinguish one value from another very quickly. So that's about dictionary. And yeah, so that's something available in Python programming language by default. So next is a tree. So trees like again non-linear hierarchical data structure which consists of large number of nodes, and for each node uh, there will be like some thing attached to that. Okay, so for each node you will have information in the form of value, and you will have references to its child nodes. Okay, and in the case of the tree, there is one more thing that I should tell you. Like in case of the tree, you will have fixed starting point. Okay, you will have fixed root over there. Okay, so whenever we discuss about tree or whenever we think of tree, whenever we try to visualize tree, the one that we are having in real world, so that tree start with root and it grows in upward direction. Okay, so in case of the tree data structure also, root is something considered as a starting point of our data structure, and instead of growing in upward direction, it grows in like downward direction. Okay, so you will have like root node in the beginning at the top. Okay, so you will have like root node over it. Draw it. There is one more thing that I forgot to tell you. Okay. So whenever we are dealing with queues, uh, whenever we are dealing with stack, we try to keep one variable only, right? Top variable. But when we are dealing with queue, we try to maintain two variables. Okay, because here we are removing element from the head side and we are adding element to tail side. So we try to maintain two variables so that we, and all of them will like for head, like one variable for the head and one variable for the tail, and both of these variable will be initiated with -1. And whenever you like remove element from this thing, you will increment like this head thing with 1, so that like it will move from this element location to this like head means this thing is empty. When you like remove element from, if there were like one element over here, and when you remove it thing, then it will move to like 0th member location, then 1th member location, 2th member location. Okay, so this is about head. And whenever you want to add over there, so it will start with -1, and you just whenever you want to add any element over there, you just increment it. Okay, so that's about queue. Whenever you are dealing with this thing, you just need to keep track of these two variables. One for the head, that something will start with -1 and it will be incremented, and one for tail, whenever you want to add element over there, it will be incremented. So whenever, if you add second element, it will be 1. If you add like another element, it will be 2. And whenever you remove this thing, it will be 1, and something like that. So you will understand this thing when you put like this thing over there. Okay, but that's about these queues and array. So in case of the trees, as I mentioned, tree is a non-linear unordered data structure where all the data elements will exist in hierarchical fashion. When I say hierarchy, that means like they will exist at some like some levels. Okay, and in case of the tree, it will start with root node. So basically this node that, or this hole that you are seeing at the top, will be considered as like a root node. And all the for that means this is a root node and it will grow in downward direction. Okay, so you will have like node over here, then you will have like few node over here. So tree is like nonlinear or unordered data structure where all the elements which are in the form of nodes will be placed in like hierarchical order, and for each node there will be like certain things. Okay, for each node, two things will be mentioned over there. Okay, so first thing is the value which will be stored inside this node, and at the same time it will also carry references to child nodes. So I'm showing them in using these lines. So basically those lines will be called as the edges, okay, or branches of that particular tree. So for each node, two things will be stored. First is a value or information attached to that node, and second thing is a reference to the child nodes. Okay, so tree is a non-linear unordered data structure where you will have like bunch of nodes. It will start with root node, and for each node, it will hold two sort of information. First is a value or information, and second thing is a references to the new to child nodes. Okay, so the node that you are seeing over here basically will be considered as a child nodes. This node will be considered as the terminal nodes because they don't have any sort of child nodes attached to them. So these are like terminal nodes. This is a child node, and this node is a root node. And for these nodes, this node will be considered as a parent node. Okay, so this is a tree. This is a tree-like structure, and here exists hierarchy. Okay, so this is 0th level. This is a first level. This is a second level. Okay, so basically there exists hierarchy, and that's the reason it's considered as a non-linear or hierarchical data structure. Okay, and one more thing about tree data structure is that you will not see cycles inside the data structure. Okay, like this node will not be connected back to this node. Okay, so it will go in like one direction only. They will not cycle back to same node again through that structure, which is the case in case of the graphs. So in case of the graphs, you will not have any node, root node.
Mayus,
Yeah.
excuse me, I have one question regarding this child node and parent node. So each parent node will connect to only two child nodes, or like there can be multiple?
You can have multiple child nodes. You can have multiple child nodes. Okay, means it depends on what kind of tree you want to build. For general tree, you can
Okay.
have as many as child node over here. Okay, it may be like 2, it may be 10 or anything. Okay,
Okay, okay, yes,
so
yes.
it depends. The reason I drew like two child nodes over here only because the another data structure that I want to discuss is binary search tree. Okay, so in case of the
Yes,
binary
yes.
search tree, for each parent node there will be just two child nodes. Okay,
Okay.
that's the reason like I added like this two child nodes over there. Okay, but yeah, that's about this tree. So tree, each element will be considered as a node. For each node there will be like two things attached to that. First is the information, and second thing references to the next references to the child nodes. And the another property of a tree data structure is that you will not see any sort of cycles over there. Okay, means it cannot cycle back to same node again, means through the structure, which is possible in case of the graphs. Okay, so you can start from here, you can go over here, you can go over here, and you can come back to same starting node, right? Which is not possible in tree. So that's the distinction between trees and child nodes. Okay, then I hope this thing is trees is something clear to you. Then binary search trees. In case of the binary search trees, okay, so nodes, so you know, like nodes is something will be connected using those lines. That's something we'll call as the branches or edges. And when you have to go from like one location to another location, one node to another node, so whatever branches that you traverse will be considered as a path. Okay, that's something will be considered as a path. Then in case of the binary search trees, so we were discussing for each data structure, we need to think of certain parameters, right? We need to think about like how easy it is to add element over there, or how easy it is to like delete element from that thing, or means how to search and how to sort that thing. Okay, so basically just to like facilitate that thing, in case of the binary search trees, what we have is we just have like two nodes, two child nodes for each parent node. Okay, inside that structure, for each node there will be just like two child nodes. Okay, and sometimes you also try to make that as like balance one. But that is the binary search tree. Is that's tree up only. Okay, all the properties that you see in general tree will be there, but thing is that for each parent node there will be just like two child nodes over there. Okay, and then this binary search tree, then somebody will ask like what is the purpose of like doing developing these binary search trees. So thing is that whenever we have to do searching or sorting, so in that situation So this is a like binary search tree that we are having with us. So if you have to search for particular element, or if you have to sort this particular tree, then what we generally try to do is we try to look for like this entire tree. Okay, so we start with root node, then we go to left node, then we check this element, then we go to left, then we again move back, then go over here, then it sees like go all the way back over here to left and then to right. Okay, so it's like a fashion of this is like depth first thing. Okay, you can also have like breadth first search algorithm over there where you will just check this thing, then you will come back, you will check this thing. So this is a DFS thing, means the way you can traverse through the tree means varies. Okay, but the thing is that if you do that startup tub, you need to visit all the node at least once. Okay, if you do like BFS, sorry, if you do DFS, or if you do BFS, you need to visit all the nodes. Means in worst case you need to visit all the nodes. Okay, so if you have to do searching operation very quickly in that situation, what, so because when it comes to trees, addition and deletion is really quick thing. Okay, it can be done very quickly, but when you have to do searching thing or sorting, so in that situation it become quite difficult, and that's the reason we go for binary search trees. Okay, so generally binary search trees, when we have to do searching and sorting, we try to convert this entire tree into array. Okay, and the array that we get out of it will be considered as a heap. Okay, and that heap is something we can use for searching and sorting, because when we get array, when we get list, it's easy to perform all those operations which are available for sorting and searching. Okay, but apart from that, whenever we are developing this binary search tree, or whenever we try to convert this binary search tree into heaps, so these there are two types of heaps available out there. One is a mean heap and one is a max heap. Okay, so what generally you try to have over there is you try to have either minimum element over here for root node, or you try to have maximum element over here. Okay, so it will either go in descending order or go in ascending order. Okay, so if we consider like mean heap, then it will, you will have like 0 over here. I'm just like putting some random number over here. Yeah, over here, then you will have like 2 over here, you will have like 3 over here, then you will have 5 over here, then maybe 6 over here, then 7 over here, and 8 over here. So basically this is how this mean heap or mean heap kind of binary search tree will look like. But whenever we have to do searching operation, whenever we have to look for element 7, so in that situation we will always start with 0, then it will like point to this direction, because that 0 is like two reference, one is to 2 and another is to 3. So for if you go for DFS or BFS, it will go to 2 first, then it will again see, oh, we again have two references, so it will go to this memory location, it will come back, because we don't have any, this is a terminal node, it will come back, it will check this, then it will move back, then it will go 3, and then it will go over here. Okay, so this is a lengthy process, and that's the reason what people generally are doing is like they are trying to convert this entire array into, sorry, entire tree into array. So we have like 7 elements over there. Okay, so basically since this is the binary search tree, we know at each level number of elements which are present inside that layer will be double. So at 0th level we have only 1 element over here, at first level we have 2 elements, at second level we have 4th element, at third level we have 8 elements over here. Okay, so what we generally try to do, we try to create array, and then we try to like put elements over there. Okay, so here I have like 5, so I will put 5 first over here inside that array. So I will put 5 first, then I will put, because this thing is sorted. Okay, so 5 6 2 actually I'm putting it everything in one location, then 0, then 3, then 7, and then 8 kind of thing. So basically we will try to have this sort of structure over here. Okay, so 5 6. So since this tree is not that sorted yet, so basically what happens when you put this thing in array, it becomes quite easier to like do this searching and sorting properly. Okay, so if you like put this thing in the form of array, you will start with like left 11, then you will have 5, then you will have 6, then you will have like 2, then you will have 0, then you will have 3, then you will have 7, then you will have 8. Okay. So this tree is something represented in the form of like array, and now you know like how to do sorting of this array and how to do like searching. Okay. And that, and you, since it's like binary search tree, you know like what zeroth index mean, what's one first index mean, what the second index mean, third and fourth and fifth and sixth, and where exactly new element will be added. When I add any element over there, by default it will be added over, then second element will be added over and something like that. Okay, so that way we can keep track of this array. Okay, first element, like this way we can like develop this thing. Okay, so basically I'm okay, sorry. So this is the mean heap. So it start with the root. So 0, then 2, then 3, then 5, then 6, then 7, then 8. And then all the element at third level will be added over there. Okay. Since it is a mean heap. It's getting quite cluttered. But yeah. Means if you just consider binary search tree, and if you write means there are various fashion in which you can like do this accessing thing. But if you consider this to be a like mean heap, then you can start with root node. You will add that as a first element. Then these two will be added over there. 2, 3, then 5, 6, 7, and 8. And next element will be added over there. Okay. And by default, that element will be like sorted. That will be like in ascending order. So that's like beauty of that particular heap thing. And heap will something allow us to do searching and sorting quite quickly. Then next thing is graphs. Okay, so let me quickly finish that graph thing. So graph is again hierarchical data structure which is similar to trees only. The only thing that's missing in, or which is additional in case of the graphs is you will not have root node over there. Means there will be no sense of like starting node or something like that. You will just have like bunch of nodes over there, and all those nodes will be connected to each other. And cycling is something allowing over there. Okay, means you can start from any particular node and you can come back to that particular node through like going through the structure, traversing after traversing through the structure. So that's the graph. So in case of the graph, each node will be considered as a vertices. All the edges or branches which are connecting these two vertices will be considered as like edges. Those edges will be directed or undirected. Means there are certain cases, right? In case of the road, like there are certain because graphs is something we use to represent maps. Okay, so in case of the roads, there are certain roads which we can take in one direction only and not in other direction. So in case of the graphs, also edges can be directed and undirected. Okay, and in some cases we can also make them weighted and is non-weighted, because that's something can be used in A star implementation of A star or D star algorithm. So that's about graphs. And then there is a hashing operation. So as we were discussing, guys, we have like less than minute left, so this call might get disconnected. So what you need to do is you need to join again using same link if this call get disconnected. So next thing is the hashing. So as we were discussing, let's say we have like a really big array and we have to look for a particular element. Then in that situation, in